Alright, so now that we are done with the introduction of RX compounds, which is alcohols, amines, and alkyl halides, with the reaction mechanisms and the Kahn-Ingold pre-log sequence, I think it's now time to specify further what's going on with the first mechanism of action, which is, again, nucleophilic substitution. So let's start. Alright. Now, there is a certain special case here when we talk about reactions of RX compounds, specifically when we talk about nucleophilic substitution. So, in nucleophilic substitution, again, we have the substrate R, then we have here the X, which is its original attached functional group, which would turn out to be the leaving group, and we have here the nucleophile. So here there are actually two options that would happen in the reaction, and it would depend on what we say the molecularity of the reaction. So when you say molecularity, how many molecules are there participating in the rate determining step? Again, let us have a review. Let's have a review of the rate determining step. So for example, I am in a car. Alright, I have here a car, and I would want to go from this place to this. I mean, from my house to this place. Don't know what kind of hotel this is, or ano build. Hotel talaga una iniisip. Anyway, now we have here the travel time. Let's say the total travel time is 2 hours, and for example, from point, let's have here a point B. This is point A and this is point C. From point A to point B, it would just take us, let's say, 10 minutes. And then the rest of the 2 hours, which would be 110 minutes, would be from point B to C. So, for example, I had a really bad traffic from point A to B. Would that matter a lot? Maybe, but this one is just too short to deal with, to consider. But for example, I had really deadly traffic here from point B to C. If I have a traffic there, then most likely it would take me much longer to get from point A to point C. So we say that, for example, this part here is the one which limits, or the one which dictates how long it would take from me to get from this point to this point. The same here. So how many steps in the rate determining step, that is the rate, or that is the part of the reaction which would dictate how long the reaction would last. For example, I have here Rx and Nu. So we say that this is the first molecule and this is the second molecule. So that means we only have 2 molecules, and we have only 2 options for molecularity in order to determine, again, the rate determining step, or which participates in the rate determining step. So if we have 1 molecule that participates in the rate determining step, well, that is unimolecular. If we have both molecules participating, we say bimolecular. And I would like to stress that when we say unimolecular, between the 2, Rx or Nu, it is Rx which participates in the rate determining step. And I'll explain it actually right now. So first, let's deal with unimolecular reactions. For example, I have here again Rx, but just to make it even clearer, I'll just draw an actual compound. And then we have, for example, chlorine. So we know that this is the alpha carbon, this one is tertiary, alright? So we know that this is the functional group, or X, which would turn out to be the leaving group after the reaction has taken place. We say that the Rx participates in the unimolecular reaction because, in comparison to unimolecular, in bimolecular, the nucleophile attacks the Rx, then X leaves at the same time. But here, what happens is that the nucleophile has no interaction because, again, the Rx is the only participating molecule. So we say that Rx first, this one turns into the part wherein Cl leaves already. So meaning the Rx here doesn't need the help of the nucleophile in order for the leaving group to leave. Alright? Meaning that this substrate has the capacity by itself to let X, this time Cl, to leave. So what would happen as a result? When Cl leaves, Cl will win the electrons over carbon. It would have a negative charge. And of course, carbon would lose. It would have a positive charge. So here we gain a carbocation. And this is step 1 of the unimolecular reactions. Again, we're talking about, let me just rewrite it down. Unimolecular reaction. Then after that, what do you think would happen? My marker just flew. So we have now we have a nucleophile here. We have a carbocation here. Nucleophile negative, carbocation positive. Nucleophile goes in, and as a result, as an end result, what do we get? Obviously, we get the product wherein the nucleophile attaches to the previously positive carbon. So this is step 2. So meaning, if we say that the Rx participates in the rate determining step between step 1 and step 2, which would take longer, since we say that this one participates in the rate determining step, this Rx. So meaning this step wherein Rx participates by itself only, this one is the longer, or the step which takes more time than this. Meaning this is just a fast step. It's as if step 1 is this travel, and step 2 is just this one. So, the rate determining step goes first in unimolecular. And we see that we have 2 steps in the unimolecular reaction. Now let's compare that with a bimolecular reaction. Let's have here bimolecular reaction. So I'll draw another compound, for example. Let's have, for example, ethanol. If we say that in the bimolecular reaction, both Rx and nucleophile are participating in the step, or in the rate determining step, well, this means that from the get-go, the nucleophile will already attack the carbon without waiting for the leaving group to leave. In that way, both the nucleophile and the substrate, or the Rx compound, will participate in the rate determining step. So what does that mean? It means that you would only consume both of this simultaneously in just one step. Remember, because once you've consumed both of this, there's no more reactants. We only have 2 molecules. So if those 2 molecules react at the same time, then that's only one step and the reaction is done. So at the end, what you want is that the nucleophile will replace the OH. Previously, this one should be negative. Now, the leaving group is the one which is eliminated or substituted. So now, how do we know if, for example, we have an Rx compound here? How do we know, or a set of conditions, how do we know if the SN reaction is uni or bimolecular? By the way, this is the shortcut for unimolecular. SN1, 1 meaning unimolecular, and SN2 for bimolecular. So how do we know if SN1 or SN2 would be taking place? Well, we have to consider several factors. Actually, there are 4. We have discussed already. No, actually, we haven't discussed anything yet. So there are 4 factors. First would be the substrate itself, which I'll explain clearly first. Then let's complete this list first. Then after that, we go to the nucleophile. Then we go to the leaving group. And then the 4th, which I would mention in a separate note, is the solvent used. So let's focus first on these 3. So first with the substrate, look, let's compare here. Let's compare this unimolecular reaction to the bimolecular reaction. So here in the unimolecular, you see that I wrote here a tertiary one, while here for ethanol, this is just a primary one, right? This alpha primary. Alright. Now, why is it that I used a tertiary RX compound in the unimolecular reaction? Look, the purpose of these carbons is to support the alpha carbon. If you look here, which of the two is more stable? Which of the two alpha carbons here is more stable? The tertiary or primary? If you say tertiary, then you're correct, because remember, the more carbons there are attached to the alpha carbon, the more stable it is, because these carbons would donate electrons to the alpha. Alright? Unlike here, the only one that could help this alpha carbon is this carbon. That's why, for example, if the leaving group leaves, let's say that chlorine is a good leaving group indeed, what would happen? Carbon here, the alpha carbon would have a positive charge, correct? The thing is, the carbon here would say, hey, I'm okay, even if I have a positive charge, if there are no electrons, I'll just borrow electrons from my neighborhood carbons. Unlike here, we only have one carbon to borrow, so most likely, what I'm saying here is that if you have a stable alpha carbon, most likely you could, have this RX compound undergo SN1 or unimolecular. Then if it's less stable, then SN2. So if you make a table here, alright, so when we talk about substrate, we use the code number 1. We say that we pick the most stable, which is tertiary, which would be followed by secondary, then primary, then last would be the methyl. So meaning that the tertiary has the highest tendency to undergo SN1, followed by secondary, primary, and methyl. While in the SN2, look at here, it would be the other way around. Methyl undergoing SN2 more than primary, then secondary, then tertiary. Alright. Now, let's go to the nucleophile. Here, you see that the nucleophile in the unimolecular reaction didn't attack the RX compound at the same time that the leaving group left. What happened is that the leaving group left first. Then the next step is the nucleophile went in. So the nucleophile waited for the perfect opportunity to attack the carbon. Alright, why? Does it mean that the nucleophile cannot handle the carbon when it has a leaving group? Does it mean that the nucleophile cannot compete with the leaving group? Yes, that's the case. Because the nucleophile cannot fight with the leaving group, it has to wait for the leaving group to leave. In that case, we could describe the nucleophile as weak, because it cannot be strong enough to attack or to counteract the leaving group. Unlike in this case, for example, in SN2, we see that the nucleophile attacked the alpha carbon even if the leaving group still hasn't left. The nucleophile here must be strong enough to say, hey, you know what, leaving group? I'm so strong, even if you're attached to the carbon, I can still swipe the carbon away from you. I could still take the carbon away from you, even though you're still attached to each other. And so, in that case, the nucleophile in the bimolecular reaction should be strong. Alright. Now, how about the leaving group? Well, we see here that we have, the leaving groups, we don't compare them. But actually, when we talk about the leaving groups, we have two factors. So, we talk about the leaving groups here. So, when we talk about the leaving group, the first factor we have to consider is, of course, electronegativity. Well, as we know, electronegativity increases from left to right and bottom upwards the periodic table, meaning that fluorine is the most electronegative. Although the possibility lies in that, for example, we have the table for halogens. Fluorine, chlorine, bromine, and iodine are very similar in electronegativity. But when we go here in the periods seen of, fluorine is more electronegative than oxygen, is more electronegative than nitrogen, is more electronegative than carbon. So for example, we compare chlorine and oxygen. We say that since chlorine is, if we assume that chlorine is more electronegative than oxygen, I cannot remember the Pauling scale values, then chlorine must be a better leaving group. So meaning electronegativity, if the electronegativity goes up, it's a better leaving group. The second is size. Again, we talked about this one, fluorine, chlorine, bromine, iodine. They have similar electronegativities, but they are different in size. Fluorine here is like this small, chlorine is larger than bromine than iodine. The thing is, when it becomes larger, there are more electrons, right? It becomes more unstable, even if it has a certain electronegativity value. The fact that as it becomes larger, it has more electrons, as size goes up, it also becomes more reactive, more unstable. And for example, we compare something like, C bonded to F and C bonded to I. Yes, fluorine is the most electronegative atom, but I is so large, it is so unstable, and the iodine would be like, hey, I'm so unstable, I have so many electrons, I cannot, keep up with you, carbon. Maybe it's better if I just leave. Unlike fluorine, it has just few electrons, and it would be so greedy with the electrons, since, fluorine has few electrons in itself, and it would be like, hey, carbon, I have also few electrons just with me. Please, I need your... No, F is persuasive. It's like, no, I'm demanding, carbon, I'm demanding your electrons because I only have few electrons left. So meaning, as size goes up, the leaving group possibility of it being a good leaving group becomes even better. So here, generality is that the leaving group should be good, a good leaving group. If it's not a leaving group, then substitution would not happen. Now, we talked about the last factor. We've talked about factors affecting whether the nucleophilic substitution is bimolecular or unimolecular. Now let's talk about the solvent. We've talked about the substrate, we've talked about the leaving group, the nucleophile. Now the fourth is the solvent. Now let's go back to the discussion. For example, I have here two compounds. I have here methanol, then let's say I have here isobutyl alcohol, and again, let's have a review. If we have here a methyl alcohol, a methyl RX, most likely it has an unstable alpha carbon, right? This one has a stable alpha carbon because we know that this is the alpha carbon, it is supported by these carbons. So again, if we have unstable alpha carbon, it's as if we use this trend. Methyl is greater than primary, secondary, tertiary, and this one is the scheme. Let's go back. This one is the scheme we follow for SN2. So most likely this one should follow SN2, and then the other way around, stable. The most stable one is the tertiary, then followed secondary, then primary, then methyl. This one should be SN1. Then what else do we have to follow? We need to have a strong nucleophile in SN2 and a weak nucleophile in SN1. So for example, we have SN2. A strong one would be, for example, NaCl. Alright, NaCl. Why? Because the chlorine here is very negative, because the Na here is very not electronegative. It has a low electronegativity value. That's why NaCl is an ionic bond, right? It's positive here and it's negative there. So let's say that this is a strong nucleophile. Although in reality, the reagent we use to add chlorine here is SOCl2. We'll get there later, but just for explanation's sake, let's say that we use here a strong nucleophile. if we use a weak nucleophile, it should usually be an organic reagent. So for example, let's just use this one. Let's just use methyl chloride as the source of chlorine, which would substitute the OH. Now, there are certain types of solvent that we could use. We could use Protic or aprotic. Protic meaning it can give out H. Aprotic meaning no H. Both cases, they should be polar. Why? Because whether the leaving group here is OH, NH2, or X, the compound will still be polar. And you know, the solvent must be polar or else it will not dissolve, because again, like dissolves like. You cannot expect a non-polar solvent to dissolve a polar solute. So again, we can either have a polar protic solvent or a polar aprotic solvent. So what's the issue with, you know, for example, let's have examples first. A protic solvent, let's say, is let's just use the simplest one, water. How do we say that water is protic? You know, oxygen here has a partial negative charge, partial positive charge. There's tendency that oxygen might release H. Or, you know, let's level up. Let's use methanol. The same thing. We have H here that oxygen could release. Then you could have, you know, hydrogens roaming around. Now, example of a protic, no H, is acetone. Acetone is something like this. HT, then CO. This one cannot release hydrogens. Why? This carbon has 3 hydrogens bonded to it, but can't be released because CH bonds are non-polar, right? As well as this. You cannot expect that the hydrogens from this bonded to carbon would be kicked away simply because the bonds between these hydrogens and carbon are non-polar. You cannot break that to produce hydrogen ions. So this is an example of a polar. We know that acetone is polar due to this carbonyl functional group, and it's aprotic because it cannot release a hydrogen. Now, what's the issue if the solvent is either protic or aprotic? Thing is, look at this. Hydrogen ion or proton is positive. Alright? What is our nucleophile? A nucleophile we have here as negative. What happens? There's a possibility that this would react with this. So, when do we like this and when do we not like this? So, just a general principle, H goes to the stronger. It's kind of a modified Markovnikov's, but I just thought of this rule. H goes to the stronger. How do I say that? Here we have a strong nucleophile. Then this one is let's say an okay leaving group, but not really a strong one. We say that, for example, here nucleophile is stronger than leaving group. Here we have a weak nucleophile. This is normal leaving group, but since this is weak, we assume that compared to the leaving group, this is weaker. So if we compare the nucleophile and the leaving group, well, nucleophile should be weaker than the leaving group. So what do we have here? H goes to the stronger. What happens when H goes to the stronger in SN2? It will go to this one because this is stronger. Then the other way around in SN1, it will approach the leaving group. So when do we like that? And when do we not? Let's go first to SN2. Let's go first to this one. Let's fold this. What happens when hydrogen bonds to the nucleophile? They will form a bond, so we form HCl in this case. Is that what we want? The purpose of this chlorine is to attach here, right? The chlorine here is supposed to attach to the carbon, not to this one. So do we want this reacting? The answer is no, because you know, if this react together, then you cannot anymore form the product you want. You want the chlorine to substitute the OH, but that cannot happen because the hydrogens being produced by the solvent are already taking up the nucleophile. So it's as if hydrogen here is blocking the way for the reaction. So here we do not want a Protic solvent here. So in SN2 we do not want a Protic solvent. So in SN2 we need an aprotic solvent. Aprotic. The other way around, let's go here. So what happens? Hydrogen here, let's draw a hydrogen here, goes to the leaving group. So let's say the leaving group leaves. What happens? The leaving group becomes negative. This is negative, this is positive. They form a bond. Do we want that? What's the point of the reaction? The point of the reaction is to have the chlorine again react to this one. So will the hydrogen help by absorbing the leaving group? Of course, because the moment that the hydrogen here attacks the leaving group or persuades the leaving group to bond to it, the leaving group would leave better, and the chlorine here would have an easier time attacking. So we want it here. So in SN1 we prefer Protic solvents.